Well, hello, we're having a look at the types of stationary points. Types of stationary points that we can have in polynomial curves, and we're going to have a look at specifically how to verify the types of stationary points using what's called a gradient table. Okay, now here's a curve up here, and what we're looking at here is a point which is called a local maximum point. It's a maximum, it's a hill, it's a mountain, okay? Notice that immediately to the left of A, the gradient is positive, and immediately to the right of A, the gradient is negative. This is what characterizes what's called a local maximum, okay? You got that one? See this down here, this is the profile that you get. The gradient is plus to the left, positive to the left, so you draw a little positive gradient line, and it's 0 on the stationary point, and it's negative to the right of the stationary point, okay? And you can see the hump mapped out there in that little profile diagram. This is a gradient table, okay? Now, this is a local minimum at point B. At point B we have a local minimum. So again, notice that immediately to the left of B, here, the gradient is negative, as opposed to over here for the maximum where it was positive. And to the right of B, the gradient is positive, as opposed to the local maximum where over here it was negative. So it's a reverse situation, okay? And again, we can draw this gradient profile diagram here, where we've got a negative gradient, 0 gradient, and positive gradient here, 4 to the left and on the stationary point, and to the right of the stationary point, just respectively for a local minimum. Okay, and thirdly, over the screen we're going to look at a stationary point of inflection. Okay, this is where you have for this example, we've got a positive gradient to the left, 0 gradient on the stationary point, and positive again. It goes up in the same direction as it was going before it decided to level off and have a little rest here. Okay, so here's the gradient diagram for that particular situation. It's positive here, it's 0 here, and it's positive there. Okay, that's a positive, well, it's a stationary point of inflection which goes from positive to 0 to positive. And the other scenario that you can have for a stationary point of inflection is a negative one, where you're going downhill. Okay, you go down and then to a 0 and then down again. Okay, do you get that? Okay, now lastly, I just want to mention here that stationary points types A and B are called turning points because they turn around from going, in this case, positive to negative, the gradients, or going from negative to positive. They turn around the other way, from going upwards to going down, or from going downwards to going up. That's why they're called turning points. It all makes a lot of sense. Now, here's an example we better do. There's two examples for us today. For the function where we've got a function such that real real values map to their real equivalents, we've got f of x equals 3x cubed minus 4x plus 1. Right, we have to find the stationary points and verify their nature, and we have to sketch the graph. Now, I should state at the outset that it's very obvious when you look at this that you don't really need to use a gradient table to verify the nature of these stationary points, but we're going to use one anyway because I want to show you how to do one in case you get asked. But look, the only situation where you can have in a cubic where, unless it's a perfect cube, something like 3 open bracket x minus 1 close bracket all cubed plus 2 or something, that's what I call a perfect cube, which has the shape of the classic cube, like the classic cube is the shape of y equals x cubed, where it's just got a stationary point of inflection on the origin, and that's it basically. This one here can't be that, because a classic perfect cube has to have if you expand it out, if it say it's what I just said before, x minus 1 all cubed plus say 2. If you expand it out the bracket, you'd have an x cubed term, an x squared term, an x term, and a number term. And this one does not have an x squared term. So it's not one of those, right? So it's not a perfect cube just translated horizontally or vertically somewhere. This one here, therefore, has to be the classic S-bend shape cube where it goes up and then down, then up again. Or maybe it's one of these cubics that just goes sort of like ones that have a stationary point of inflection, except that the point of inflection isn't stationary. So like this shape, where it doesn't actually level off at the point of inflection. Okay, it's not a stationary point of inflection. So just looking at this cubic, I can tell you that it's probably the traditional S-bend type, and if it's a positive cubic, which this is, with a +3 coefficient outside the x cubed term here, if it's a positive cubic, then it's going to have if there's two stationary points, which we'll find out in a moment by just finding the derivative of this function and setting it to equal 0. If it does have two stationary points, then we'll know that the first one has to be the max and the second one has to be the min. So we don't need a gradient table to verify the nature of these stationary points. However, I'm going to show you how to do one anyway, just in case you get asked. Alright, that's the deal. That's the nature of the game in this video. Now, okay, there's f of x, there's f dashed of x. Now we're going to set this equal to 0 for the stationary points, and there they are. X is going to be plus or minus 2/3. Okay, now they're asking us for the points with an underline there, because if they ask you for a point you need x comma y, otherwise you are wrong. Okay, they didn't ask you for the x values of the stationary points, they asked you for the stationary points, so you need the x comma y and in brackets, right? So we'll get the y coordinates. There they are, just believe me, I've worked them out. Okay, so there's our stationary points. That's our first answer. Now, the second bit of this question is we have to verify their nature. Okay, so let's do that. Now, to verify the nature, we need to test. We need to test f dash of x on either side of the two stationary points. Okay, but I can tell you automatically that this one is the max and this one is the min, as per all the palaver I was just saying before, explaining the way cubics are. Okay, so f dashed at -1 apparently is +3, and f dashed at 0 is apparently -4, and f dashed at 1 is apparently +5. Now, why did I choose those particular values? Well, I needed to choose something to the left of -2/3, and -1's a nice easy number to choose. I needed to choose something in between them, and 0 is a very nice easy number to choose, and I needed to choose something to the right of this right hand side one, and 1 is again a very easy number to choose. So you go easy on yourself, choose nice easy ones, particularly if you're in a tech-free exam. My goodness, don't go choosing anything complicated. Now, therefore a gradient table summarises these findings effectively, and we go like this. Okay, we've got x, now we've got x, f of x, and f dashed of x, isn't it? Yeah, sorry, f dashed of x. They're the two stationary points, and these are the values we've got of those other points where we just worked them out down here. And here is the shape, profile shape. Put the slopey bits in first, then put the stationary bits in to match so that they look sort of continuously flowing onwards. You know, this is a sort of an upper little dash here, and this is a little lower sort of dash here, so that it matches the likely profile of the curve that you're getting. Okay, so you can see very, very clearly here that this is a max, this is a min, as we predicted. So therefore, when x is -2/3, it's a local max. When x is +2/3, it's a local min. Well, we've verified their nature. Good heavens! Now we've got to sketch the graph, which is all very a lot of extra work. So for the graph, we need the axis intercepts, don't we? So we better do that. Now, when x is 0, y is going to be 1. Okay, when x is 0, y is going to be 1. When y is 0, we've got to work it out what x is going to be. They're the x-axis intercept we're coming up with now. That's the y intercept. Now, okay, so I'm guessing and checking here. I'm guessing and checking, but it's really not too hard to guess. Look, because if I choose x as 1, what made me choose x as 1? Well, usually you start with 1 or minus 1. They'll usually come out pretty easily, particularly in a tech-free exam. See, look, 3 plus 1 minus 4, if x is 1, comes out to 0. So that, I didn't need a lot of intuitive powers to work that out. So therefore we get that. So x minus 1 is a factor. Okay, so therefore now I'm going to use my alpha technique, as I've used in previous videos, to fully factorise this now. The reason I do this is because I don't like polynomial long division, and we know that the front terms here give rise to the front term in the expanded version, and the back terms here give rise to the back term in the expanded version. And the middle term, therefore, is the only one we don't know, because you know that 3x squared times x must give 3x cubed, and if this is a minus 1, this must be a minus 1 here to get you a plus 1 there. Do you get that? Good show. Now, expanding x squared, just the x squared. I've chosen x squared in the right hand side, but you could have chosen anything. You could have chosen the x term as well. I've just chosen the x squared, to just the expansion on the right hand side only, and then I'm going to equate coefficients with what's over here in terms of x squared, where there isn't any. So the coefficient of the x squared term over here would be 0. Yes? Okay, so what did we get now? If you multiplying this by one of those terms in that bracket there will get you an x squared term. So let's think about that. This times this would give you an x squared term, and this times this would get you an x squared term. So that's how I got that, right? So that comes to alpha minus 3 times x squared. So therefore that must equal, as I was saying before, the expanded version has no x squared term, so therefore you've got 0 x squared equals alpha minus 3x squared, and therefore 0 equals alpha minus 3, and therefore alpha equals 3. Okie dokie, got it? Now we've got it now, look. So all we're going to do now is get this into linear factors, and then we've got all of our 3 x-intercepts. Actually, I don't think this is going to be very nice. So why don't we just set this thing equal to 0 and do a quadratic solution on it? Yes, and work out what the x's would be. Good heavens. And there it is, yes. And that won't simplify anymore, because that's just 3 times 7, and both of them are primes. So I think we could say that's a half, that bit. So it'd be a half plus or minus root 21 over 6. Yes, that's right. Okay, and they are the other x-intercepts, right? That's what we're doing. I've worked them out as decimal approximates for graphing purposes, just so that I know what I'm doing properly on the screen. Okay, I know what I'm doing properly on the screen. And I've got all the proportions right, otherwise my graph could be very skew-whiff and a bit crazy. So here we go, we're nearly there now, guys. And there she be, there's the first one, that's the x-axis intercept, the first one we found by the guess and check. That's the other one we found by the quadratic solution. That's the third one we found by the quadratic solution. And this one's our max at x was minus 2/3, I think it was, wasn't it? Yes, this is the min at x is plus 2/3. We'll put those in, although you normally aren't required to put maxima and minima in unless you're asked to. If you're asked to sketch a graph, you just have to do the axes intercepts, okay? And any asymptotes, of course, and label them, but there aren't any in this case. So therefore that's our y-intercept, and I'll put the max and min in, but remember you don't have to do them unless you're asked to. I'm just putting them in here to make everything look very complete so you really get it. Okay, here we go. Yes, and yes, alright? And there it is. There's everything for you. Okay, now I just want to go back and show you this gradient table. So I'm flipping back a screen before we finish up, right? Now, see this gradient table here. You must, did I say that enough? You must put the values of the gradient in here to prove that you've actually done it, okay? Don't just go putting x and then sort of like a positive here, a negative there without a value. You must put the values in if you want to get marks in a SAC for these gradient tables and verifying using gradient tables, okay? So please don't forget that. I've marked SAC after SAC after SAC where students have got that wrong. Because they've sort of said, oh yes, this is positive here, this is 0 here, this is negative here, and we don't actually get to see any values. So we can't really know whether the student is trying to put one over us or not. So, you know, I trust you, okay, but you know, some students get a little bit stressed in SAC situations and they try to pull a Swifty, so you can't do that. You've got to come up with all the goods. So don't forget those values, put them in. That's enough of my rant, and I think that's it for now. Have a wonderful day and all the best, and we'll see you in the next exciting instalment.